Good afternoon, and this afternoon we're talking about challenges and some of the challenges that I'm having at the minute. So as you're well aware, I have been working on this billet pump idea for multiple reasons. I think I've explained a few. It's not just the performance gain that we're doing this so that we have more options in the future to be able to basically manufacture our own pumps. Anyway, obviously, machining something like this has been quite a task, as you can well imagine. And our brilliant CNC guys have done an excellent job. However, as we're testing this product out, you might have seen the pink engine the other day that I was talking about on Facebook. We'd got the completed billet pump on this engine. All ran well, no issues in that respect. I just wanted to make a few little tweaks, and when I took the back cover off the governor housing, I noticed that the oil level inside the pump was quite high. Now, if you don't know, the oil supplied to these injector pumps, it comes from a hole in this actual piece of block, and it's fed from the main oil gallery. So it basically pumps oil through this hole, and then it actually pushes it around the front of this nose piece here. There's an O-ring behind, down there into the camshaft, and it thrusts it into the actual pump itself. So getting the oil into the pump, not a problem. We can easily replicate what the original one had, but getting it out, I never thought would be an issue. However, it is an issue. So back to the drawing board, went and had a look, see what's going on. The question, I suppose, is how does the oil get from the pump back into the engine after it's been pumped in? Well, I'll show you, look. So if you look at the front of this, there is a slot here and a slot here, and they have a corresponding slot in the actual cast housing of the injector pump, right? And if you actually look, the mismatch in that is actually terrible, but that is how they are from the factory. So the oil comes back out of those holes, and if you notice, they're above the level of the camshaft. So it always kind of keeps that nice lubricated camshaft sat in a bath of oil. Great stuff. So I'm looking at mine, you know, our machined version, and the ports, the actual sizes of them, the volume of them is the same. So, and they're in the right place. You know, it's not like those ports have been put in the wrong place and that they don't line up or anything like that. So I'm thinking, what on earth is it? Why is it not working? Anyway, I had a bit of a closer look at this factory example, and I noticed, I need something to point with, and I noticed that just here, if you look, there is an angle, and it has like almost like a taper inside. And then a little bit like a light bulb moment, I realised that the camshaft that actually spins inside that body, which rotates, you know, with the direction of the engine in a clockwise manner, that camshaft, as it's spinning, is basically turning the whole passage of oil, the whole volume of oil inside that casing into one just spinning amount of fluid. So those slots are actually shaped to capture that rotating fluid and basically eject it out. So it works almost like an oil extraction pump, like a screw pump. Apart from the actual pump is not the screw, the oil itself is been spun, and the screw thread in reality is the body. So, back to the drawing board. Well, not back to the drawing board fully. The body's still good. So what we've had to do is, if you come and have a look, I'll show you one that we've machined, or we're in the process of machining, to make this theory a reality. So you can see this one is back in the machine, and basically what I've done is, not only have we made this, so you can see the comparison between the two, not only have we put that sort of taper in there to capture the oil at the angle that it's been spun, but I've also made that passageway a little bit larger. So if for any reason I can't make it as effective as the cast one, because obviously I have machining limitations, then at least I will have get the volume back by actually having a larger passageway. So, and the actual pump itself that was on there, like I say, if I hadn't have looked into it in that depth, no one would have ever known and it'd have been fine, you know, but I wanted it to be as Mercedes intended. This is the one that was obviously on that engine. So what we did is I made a few tiny tweaks to the governor on the actual engine, just because I wanted to make the idle at a more perfect position. And then we've put it back on the bench and recorded that data. And we tend to do that as often as we possibly can. Put a pump on an engine, run it, put it back on the bench. That's one of the beauties of what we do here, you know, all the pieces, not just building pumps. We're kind of building them, putting them on things, and then relaying that information and constantly learning from it. I mean, customers can give you feedback, but it's not the same as obviously hearing it for yourself in your own place, under your own conditions, and then putting it back on the bench. So, this one's now going to be disassembled, and it's going to have that modification done to it. That one, the one that's on the machine, is going to go back on the pink engine. And this one, we probably won't touch. How many of these is there? 5, 9.
5.
Well, originally, the plan was, the planets, as you can see on the side of here, that was the actual amount of pumps that there was supposed to be. 9. And again, we came across a slight machining issue where we couldn't put the plaque that actually designated what each of the planets were in the place I originally wanted it in. So the first one was going to be Mercury, you know, etc., etc. And they were all going to be plaqued up and then anodized in different colours to match the planets. That didn't quite work out because where I originally put the plaque, we had to make a modification and change the body. So I might be able to squeeze it somewhere else on it. But the amount of time and effort that goes into making something like this project's been underway for what, a year? Start a design to actually get into this stage. It will be
A year and a half.
a long time, a long time. Anyway, so that's an update for the day on what is happening with these amazing billet injector pumps and the complexities that you would never consider that go into them. Mercedes and Bosch and whatever, yeah, wow. It's never take for granted what they did. It's very impressive. Bye for now. Hello, right, so we're going to talk a little bit about the billet pump and the benefits and some of the positives that just designing and building this billet pump will benefit you as customers for all of our other equipment. So first of all, what I'm going to touch upon is the camshaft in this pump. Now, we obviously needed a supply of camshafts for these that was going to be somewhat repeatable. We weren't ready to make a custom cam at this point. So we decided to use the EDC camshaft from the electronic EDC pumps, which we've done with quite good success. And something that we discovered whilst developing or should I say modifying an EDC camshaft to work within a mechanical pump was that many customers were sending in pumps that had corroded cams, worn out cams and things like that. And I was having to give them the bad news, the camshaft's shot, and unfortunately these days you can't buy a replacement cam. So it was a case for those customers of having to send us another call, which is sadly it's a bit of a waste. So we realised that this camshaft that we'd done for the billet pump, we could actually also utilise on customers' regular pump bills. So that was suddenly a massive bonus. That helped like a lot of people. So that was quite a nice positive of doing that. And as we discussed about cam wear in the last video, the cam profile in the last video, the EDC cam profile is pretty much identical to the RS203 cam in the later style pumps. So really good, works very, very well with 6mm elements, of course, because it was designed for 6mm elements, and just a generally better cam profile for certainly smaller elements than the old 156. Not going to say it's going to have great power gains. Yes, maybe when we're knocking on the door of 1,000 horsepower, we might see some gains from using this with the bigger elements, but at the sort of 600 horsepower figure that we're generally aiming at the minute, with our other supporting bits for the 606, yeah, it works well. So that's an interesting thing that the billet pump has given to the 606, the pump building community, is those cams. The next thing is, as you can see with these billet pumps, they have a removable front section. This section unbolts. Now, it's a very commonplace issue for people to have broken lugs on regular pumps. You know, on one of these castings, I very regularly see this lug snapped off, or this one snapped off, usually down there where it's weakened, because people drop them, or the most common reason is when they're installing them onto the engine, it's not quite even, and they tighten one of the bolts to try and pull it in, and it just shears the lug off. So, I had a bit of a brainstorm, and I thought, hang on, these front sections that we've been using on the billet pumps, what if we can machine off the face of a cast pump that's damaged, that's got a broken lug, and actually, you know, reinstate it, make it worth using again. So that's exactly what I've done here. So this, you can see this casting basically uses the exact same end profile as a billet, solid billet injector pump, and we've fortunately managed to even miss all of the bolt holes and the galleries with the O-ring, because this front section is O-ringed on, to the front of the pump. So that's a big deal. Like, you might be thinking, well, who's that even going to affect? Well, look, this is just a few of the pumps that I've done just recently to repair them. So it's very beneficial. You got to consider that each one of these cores with a broken lug may have been worth £300. Well, yeah, it doesn't take much mathematical skill there to see that, you know, I'm saving somebody some money. And the big benefit is, once you've had your core converted over to this, you can drop it as many times as you want on the front flange, or, you know, unevenly tighten it, and this can be just replaced. These are something that we make. We've got lots of them in stock, so that can be done. So that's quite exciting. So that's two things that the billet pumps brought to us. Also, one of the other things is the knowledge of the actual pump internals, something that I've actually come to learn recently. The tolerances, the machining tolerances were quite fine. Obviously, you've got to consider that inside here, where the actual follower goes inside, there is quite a tolerance required. And also where the element sits, where the shoulder of the element sits into the body, that height consistency is very important. Now, what I have learned is, as you may already know if you follow our other video, that to make the phasing absolutely perfect, because I like the phasing perfect in these pumps when they go out to customers, we use phasing shims, well, a combination of changing rollers or phasing shims, to basically make sure that when each cylinder fires, it has a perfect 60 degrees of space between the firing. That's how it should be. And basically, if you assemble a regular pump with no shims and pay no attention to the rollers, you might find it's a degree or 2 or 3 degrees out of the pump, which then doubles and becomes, you know, 2, 4, 6 degrees out of the engine, which does make it run badly. Well, I had a theory. Obviously, when building this billet pump, I thought, you know, we're really going to find out how accurate our elements are, or how good the quality of the elements are, because this bad boy is super accurate when it comes to the height between the camshaft centerline and the height in which the elements sit. So they're all going to be pretty even. Well, sure enough, when it came to phasing up this one and the other ones, they required 0 shims. So they had even rollers put in the bottom into the camshaft, all equal size rollers, and they all phased up within, you know, 0.1, 0.2 of a degree, which is like amazing. Like, that's very, very good for like a straight out of the box item. You can't do that with the castings. So what we learned obviously is that the elements themselves that we're using, the accuracy is accurate, is very good, as we had expected, as we had hoped, but the body is also. So sadly, the thing is with the casting, and especially castings, some of these are as old as 1986, that you are going to get some deflection. It's gone through a lot of heat cycles, and that is why we phase them. I mean, I don't know if I showed it in my video the other day with the 2 old pumps on there. I showed the actual phasing. I don't know if I showed it, but I just checked the phasing on these standard pumps, and they weren't very good, to be honest. There was like maybe a degree of inaccuracy, which is not great, and not something I'd send out to a customer. So it shows that the bodies are perhaps deforming in use over time. So that's another benefit that we've learned, is that, you know, ensuring that our element accuracy is up there. So that's 3 good things. Now, the other thing that I've also realised is you've got to consider with that larger element, when we're comparing the original, which fell on the floor, that's actually not an original. That's actually a very bizarre 6mm with a dead slot in it. When we're comparing that to an 8.5mm element, the amount of extra pressure and pain that's on that barrel from the forcing extra fuel in is quite considerable. So what we've done is beefed up all the area, all the surrounding area, and the back side of the pump to be able to support that pressure. Because if you think about it, this open section here, which is the same in a cast body, it leaves quite a vulnerable area to sort of try and spread. If you picture it trying to spread with the pressure of the plungers lifting, it's going to try and spread the pump apart. So we've added a lot of extra rigidity and strength there, because you don't just have to consider it over time bending it, but, you know, as a freeze frame, you imagine it as it's happening. If that body's flexing, you're going to lose some of that CC. You've only got 6.9mm of cam travel, and if it pushes that casting by a couple of points of a mil, you're gonna have issues, you know. So the extra rigidity in the body is going to benefit us, I think, in the long run, as we're trying to push power numbers and accuracy of fuel delivery. So what else? Well, we've gained the obvious factor, haven't we, of the fact that the billet pumps do look incredible. And is there anything that really says to a customer or anybody watching more about the dedication of a company? I know I am blowing my own trumpet here using the word dedication, than to go to this amount of effort. I mean, bear in mind, there isn't going to be many of these sold. It's going to be quite a rarity, I think. But to go to that amount of effort and that amount of understanding of how everything works, just for the sake of learning a few things and making a cool billet pump, I hope that stands out for the customer, stands out for the people that are watching. I aren't just doing this because I wanted a pretty pump. I wanted to learn about the different. I wanted to learn about the tolerances, the bearing sizes. I wanted to know about the camshaft centerline distance. I wanted to know about, could we stretch a bit of rack travel and things like that. There was a lot I wanted to know, and there is nothing that tells you better than actually making the thing from scratch. There was a lot more than I expected went into this, to be honest. But yeah. So, is there anything that I've forgotten? I'm about there. Oh, there is one thing. A little niggle that is with a standard pump. Follow me. You see this little cap on the front here of this standard pump? This little cap here. They're like a pressed on the... that's it. It's under rack and gov cap. These little push-on caps that go onto the front, let me show you where it goes. It goes on, look, it's where the fuel rack comes through the front. This little cap, it has an O-ring, and then this little cap sits over the top. You pop it on. This one is particularly beat up. But anyway, when you've put it on, you peen the side of them to stop them coming off. And I think that they're horrible, crappy design. Because if that ever leaks, and sometimes it happens, it's quite hard to get it off to replace an O-ring or to replace it from the outside. It's nearly impossible. And I just think a bit of pressed tin like that is just very crappy. Don't like it. So when we did the billet pump, we basically redesigned it as a solid section. And this is very similar, I think, no it's not. It's a little bit similar to the OM617 version. The 617 version is a bit like that, but it has a screw-on cap. But we had such restricted space between here and the front of the actual where the engine is, so we couldn't go too big. And remember, as I said at first, I'm trying to get the maximum rack travel I can get in there as well. This aperture is slightly larger and the overall travel is larger than a standard pump. So that was a nice little feature. Oh, another nice little feature, where the fuel lines go in and out, we have replaceable brass bungs, which was quite nice. Replaceable brass inserts. So the original steel ones, they have been known for coming loose. If you over tighten them and then when you try and undo them, they come loose. And if you look, they don't have any method, there's no flats or anything, you can't get a spanner on them. So they're a bit torturous. Oh, I'm thinking of all the benefits all of a sudden now. The other benefit is we greatly increased the aperture of fuel supply. So this, if you imagine, you can see I've got the end bung out. You can see inside here, it's kind of like a cathedral sort of style. And the fuel comes in here, and it goes through there, and it goes to each element, and then comes out the back. Now, with certain elements, depending on where the inlet hole is, they're rotated quite far around, and the fuel flow to them is poor at best. So what we did is we increased that with this billet design. You can see the hole is much deeper, much larger. It's got a really, really good sized fuel rail, I would call it. So nice fuel feed abilities. I think that's about it. I think that pretty much covers it. The next step that we're going to do is obviously the billet back, because we're still using a regular bolt pattern for the regular 603 and 606 style governor. It's got a few custom pieces in the governor, but the governor for all intents and purposes the same shape. So we're going to do a billet one of them next, but it's baby steps. This is complicated stuff, and if you want to do it right, you've got to take your time and test and test and test and test. But from me and all these casings that are going to have happy customers, it's goodbye.